Yeah, so Matt wanted an interesting tidbit. So yes, that's something I started in my astronomy travels, was I realized the world has a lot of Fanta flavors. They get very odd very quickly. Japan has over 20 flavors. I'm just giving you random information. All right, so I will get started. So I'm very excited to be here. So I've had the pleasure of visiting Flatiron several times through my sabbatical, and it's been lovely talking to all of you. And I'll be visiting more, so I'm happy to chat with you if I happen to have missed you, or talk to you again. I like, I like catching up and thinking of new ideas. So I wanted to tell you. I don't want to. I'm good. Thank you. Can everyone hear me? Okay. Yeah. Okay. So I wanted to tell you about the importance and challenges of assessing stellar feedback on the scales of star clusters on up, so star clusters, GMCs, giant molecular clouds, and galaxies. And if you haven't seen my talks before, I always start with my conclusions. But before that, I wanted to tell you the people who have contributed to this work. So these are the lovely people who are part of my group and have contributed, postdocs and graduate students, as well as one undergraduate. I also have a number of wonderful collaborators who have contributed, and some of the work that I'll present here is from the FANGS team. FANGS is the physics at high angular resolution of nearby galaxies, and FANGS was initially an ALMA survey, but now we have also taken data with a bunch of other facilities, including MUSE, HST, and now JWST. So we'll have some JWST results here as well. So, all right. So the conclusions for this talk are that stellar feedback, which I define as the injection of energy and momentum by stars, is important on both large and small scales. And because it's involved in so many different scales, that's one of the challenges in terms of assessing feedback, but there are other challenges as well. So the need for observational constraints, the question of where and when energy and momentum are deposited, and then finally the fact that there are many mechanisms that must be considered, and these mechanisms happen to vary in time and conditions. And really, in the last 5 years, there's been a lot of progress in terms of coming up with observational and theoretical solutions. And so I'm going to go through these challenges and what the solutions to them are, both from a theory perspective and from an observer perspective. As Matt mentioned, I'm personally an observer, but I really like theorists, so I think it's good to talk about both. And in general, my solution as an observer has been to use multi-wavelength observations to assess the comparative role of feedback. So I started by working on H2 region scales and looking at how these vary with different properties, such as stellar age and conditions. And now I've actually moved on to larger scales, looking at how feedback gets gas out of disks and launches galactic winds, and how on galactic wind scales, we're beginning to look at the hot gas properties and getting some of the important constraints there, and looking at the relationship between the different phases and how it indicates that there is mass loading in galactic winds. So that's the sort of play-by-play of what we're going to hear in the next hour. Feel free to ask questions. Okay, so in general, stellar feedback is important on many different scales. It's sort of one of these very interdisciplinary topics that incorporates basically all of astrophysics. And it was identified in the late 1970s that you need stellar feedback in order to produce realistic galaxies. And so if you had something that should look like the Milky Way, but you don't incorporate stellar feedback in your simulation, you get a galaxy like the picture on the left. So you end up with a stellar mass and bulged mass that's about 10 times too big. You have too many stars there in the center and not enough gas coming further out. However, if you do incorporate stellar feedback, then it removes gas from the center, produces the extended disk structure, and we get something that looks much more like the Milky Way. So really, there's a lot of different ways that stellar feedback is important. Besides producing spiral galaxies, we also need them to produce other kinds of galaxies, such as bulgeless dwarf galaxies. It's important to produce observational relationships like the galaxy luminosity function, the mass metallicity relation, the Kennekitt-Schmidt relation that regards the star formation efficiency on galactic scales. And then it's also important to produce or lead to the launching of galactic winds that produce pretty pictures like we always see of M82. On smaller scales, which I'm defining here as less than 100 parsecs, so giant molecular cloud scales are smaller, you need feedback in order to produce a multi-phase structure of the ISM to get the low star formation efficiency in GMCs, to account for the life cycle of GMCs, the fact that they are disrupted and destroyed on tens of megayear timescales. You also need it to drive turbulence as well as to trigger star formation. So there's a lot of different things that come into play. A lot of times when we talk about stellar feedback, or at least if you talked about it 30 years ago, I think people only thought about supernovae as the primary mode of feedback. However, there are many ways that stars deposit energy and momentum. And so let's go through them. So in the star formation process, you have protostellar outflows and jets. These are particularly important in star clusters where you don't have massive stars. Then when you do have massive stars, then during their main sequence lives, there are many processes that are important, including radiation, both the radiation that couples directly to the gas, as well as the radiation that is dust processed. We have photoionization heating and stellar winds as well. And then finally, in the final throes of a massive star's life, you have supernovae and then cosmic rays that are accelerated by the supernova shocks. And I want to mention here cosmic rays because there's really been a ton of work in the last 5 to 10 years about the role of cosmic ray feedback. And this is my little summary slide for why they're important. So in general, we think that something like 10% of the kinetic energy of supernovae goes into accelerating cosmic rays. I also think that stellar winds and AGN are important in cosmic rays as well. And there's been a lot of simulations incorporating cosmic rays, showing how the different ways that it's important. The first paper that got me excited about the topic was one by Craig Booth in 2013, who looked at cosmic ray feedback versus thermal feedback in an SMC-like galaxy and a Milky Way-like galaxy. And you can see automatically that these look very different in their profiles in terms of what's happening to the gas in the disk, as well as in the outflows. But in general, these are sort of the 4 summary points. So cosmic rays can drive galactic winds. They affect the properties of the winds. So these are going to be cooler, more multi-phase, and accelerated more gently. Cosmic rays in the disk of the galaxy can suppress star formation. And on larger scales, they also influence the CGM properties. You end up with a cooler CGM that is more metal enriched. So I gave no references here. That's because there's a lot of them. And it's especially exploded in the last 5 years, like I said. Yeah, it's a lot. And I didn't even highlight all of the Phil Hopkins papers. There's really quite a lot. I just kind of kept adding the letters. Anyway. All right, so, okay, feedback's important. It's also one of the biggest uncertainties in star and galaxy formation models today. And I think this stems from sort of 4 different challenges. And this is really the crux of my talk. And we're going to go through what those 4 challenges are and the solutions. So feedback challenge number 1 is the dynamic range. So the fact that you're dealing with processes that are at the scales of individual stars and star clusters. The star clusters are maybe a parsec across. then those are influencing the life cycle of giant molecular clouds, which are like 100 parsecs across. And then those shape whole galaxies on tens of kiloparsec scales. So in terms of solutions for dealing with this dynamic range observationally, it's good to study Milky Way and nearby galaxies where all of these scales are observable. So you can get down to the individual stars, but all the way up to the large scale structures of the galaxies and see the influence. In terms of theory, I think that getting parsec scale resolution is important. So I think zoom in simulations have helped a lot in order to understand the impact of feedback. So of course, now we're in the era of JWST. And so this is giving us a new resolved view of infrared emission. And so I wanted to mention some of the advances that we've had with JWST, particularly showing some of the new results from the FANG's JWST survey. So FANG's JWST is observing 19 star-forming galaxies. 10 of these have been observed already. 5 have been reduced, and the other 5 are basically were observed like in the last week or two, and so they're in the process of being reduced. The 5 that we've reduced are the ones listed here, and we've written something like 25 papers on the first 4 galaxies that were observed on this list, and these 25 papers were all published this week in a special issue of AppJ. So the paper that summarizes the goals of the FANG's JWST program was written by Janice Lee. So that's the one to look at if you're like, okay, please give me a summary of what is happening. I don't want to read 25 papers. But really, as you know, we have a lot of pretty pictures, a lot of data, a lot of different science that we can do with it. So this is one image of a particular galaxy. It looks like a fire simulation, but it's a galaxy, a real galaxy. And so we're doing a lot of different things with this beautiful data. This is a picture of NGC 628, a phantom galaxy. And this is another image from Janice's paper showing the comparison of Spitzer data versus JWST, where you can see the improvement in the data. So you obviously see a lot more blobs on the right compared to the left. So we have an order of magnitude better spatial resolution, order of magnitude better sensitivity, and that gives us a lot of capabilities for science that we didn't have before. So one result I wanted to highlight from these papers was related to feedback is looking at bubbles in NGC 628. So one of the targets. And so there's this nice paper by Watkins et al. Who did an inventory of the bubbles in NGC 628 from this JWST data. She found 1,700 bubbles in the image, and they range in size from 5 to 500 parsecs. And so the cyan shows you what these bubbles look like. These were actually done by eye, so you can do a lot more if you did it maybe in a more systematic way. And also, this is only from one galaxy. So I think we're gonna have a very large statistical sample once we have, all 19 galaxies or, all the rest that will be observed with JWST. So one of the there's a lot of interesting things here, looking at the morphologies of the bubbles, how they're related to the stellar populations, their locations in the galaxy, where they are in the spiral arms, etc. But one thing that I found interesting was that something like a third of these bubbles have bubbles at their rims. So if you zoom into bubble A there, you can see that there's all these little bubbles along the edge. So that's evidence of triggered star formation. You have additional new star formation that's occurring as the bubbles go outward. And so there's a lot that we can do with this. And the complementary multi-wavelength data lets us learn a lot about the evolutionary sequence of bubbles and and the feedback that is shaping them. Okay, so feedback challenge number 2 is the need for observational constraints. So we highlighted 6 different feedback mechanisms. And in order to constrain them observationally, you actually need a lot of different multi-wavelength observations, going everything from radio up to X-rays and gamma rays. So this means that you need high quality data across the electromagnetic spectrum in order to constrain them. And fortunately, we do have that. So this is another image from the Watkins paper that shows all of the different multi-wavelength images, which are arc-second or better spatial resolution that we have from everything from ALMA to VLA to HST to now the JWST images. And I like to kind of summarize the need for multi-wavelength data with this little cartoon of an elephant. And it shows people investigating their part of the elephant that's nearest to them. And they think, depending on what part they're investigating, they say, it's a fan, it's a spear, it's a snake, it's a tree, it's a rope, it's a wall. But really, it's an elephant, right? And it's because they're just looking at that one part that they're misinterpreting it. So I think this analogy extends to astronomy because you need multi-wavelength observations to get a full view of the elephant. The elephant is the galaxy in this case. Otherwise, we're going to think our galaxy is a spear or a snake or a tree. So that's why we need multi-wavelength data. In terms of feedback, however, there is another way to assess feedback observationally, and that is integral field spectroscopy. So you can actually get a lot of the information just from optical IFU data as well. So feedback challenge number 3 is the questions of where and when the energy and momentum is deposited. So the where question comes back to the issue that stars move. We've learned a lot from Gaia, and one of those things is, yeah, stars do not stay in the same place. And in general, massive stars are very mobile. So something like 50% of O stars and 10% of B stars are runaway, which means they move faster than 30 kilometers per second. Many more are walkaways, which is greater than 10 kilometers per second. And if you calculate that and say, okay, the typical lifetime of an O or B star is 3 to 50 megayears, that corresponds to traveling 50 to 500 parsecs before they explode as supernovae. So that means that many of them will actually explode in a very different environment than where they formed. It means their feedback will be deposited differently. And so one example of this, or one impact of this, for example, is the higher escape fraction of ionizing photons on massive stars. So there was this really nice paper from 2014, which showed the density distribution for runaway stars in red versus non-runaways in green. And you can see that the runaways have a much more uniform density distribution, which means that they can actually occur in much lower density environments than the non-runaways. And this causes, again, for them to have higher escape fractions of their ionizing photons. So the fact that stars move impacts where they deposit and how they deposit their feedback. So in terms of theory, I think a nice thing to do is just say, okay, what is the impact on the observables if I shift, for example, where the supernova occur? So there's a really nice paper by Steffi Walsh in 2015 who placed supernovae in different locations. The top is that they had a random distribution in a galactic disk. The middle was that they were located at the peak of the density field. And then the bottom is if they were clustered. So 50% were at the peak density field and 50% were randomly distributed. And then she looked at how does this impact the gas in the disk and the outflows that are produced. So these were the outcomes from those simulations, looking at what happens to the gas density, column density, and temperature if you have randomly distributed supernovae clustered supernovae, or supernovae that only occur at the peak in the density field. And so you can see that when the supernovae only occur in the disk, you basically have no outflows, everything is very concentrated. Whereas in the random case, in the clustered case, you have much more gas that's able to get out. And these are much more representative of what we observe. So in terms of observations, we can kind of do a similar trick, which is let's just look and see where supernovae are in relation to the dense gas from which they formed. And so there's a really nice paper by Ness, Maker, Chen, where she looked at ALMA data, specifically the FANGS ALMA data, and compared or looked at the locations of something like 60 recent supernovae and saw how close the supernova were to dense gas, to the CO. And so this is one map example of NGC 4303, where there were many recent supernovae. And, but again, she looked at 60 sources, and this was the results. So she found that the relationship to the dense gas actually depends on what kind of supernova it was. So 85% of the type 1 BCs happen coincident with CO clouds. 40% of type 2s are coincident with CO, and 35% of type 1As are coincident with CO. So I think one thing that was kind of surprising with this result was that type 2s and type 1As are actually not that different, whereas type 1 BCs, they're really going off in the dense gas. So this is because probably the lifetimes of type 1 BCs are shorter than type 2s. But still, this gives us an observational constraint on how many of these different kinds of supernovae are going off, you know, within the clouds that form them versus have traveled outside of the clouds before they explode. Yep, of course. So the stars on the rim are going to be younger, are more newly formed. The bubbles can be formed from supernovae or from pre-supernova feedback. So yeah, so the littler ones might be the pre-supernova feedback. Yeah, or more recent supernovae. Yep. Okay, so let's see. So an interrelated question of where is the energy momentum deposited is when is the energy momentum deposited? And so we can actually try to answer this question observationally as well. So this is a nice paper by Melanie Chavant from last year, who took the FANGS ALMA data of 9 galaxies and saw how disrupted the molecular clouds were as a function of stellar age. And so these show the feedback time scale as a function of stellar mass, metallicity, and GMC surface density. And Melanie found that in general, the giant molecular clouds were disrupted on 1 to 5 megayear timescales. Now your timescale for like a typical supernova is 3.6 megayears. So that means that if these are disrupted in shorter time, then pre-supernova feedback can be very effective at dispersing these clouds and disrupting them. So pre-supernova feedback can actually be pretty effective at getting rid of that molecular gas. Okay, so feedback challenge number 4 was the fact that there are many mechanisms that have to be considered. And of course, you know, this is a challenge observationally and theoretically. Theoretically, we can begin to assess the role of different mechanisms by seeing how the different mechanisms, for example, produce different galaxies in simulations. So there's been nice work, the Aquila comparison project, the Agora simulations as well. So the Aquila comparison project, they did 13 Milky Way-like galaxies and compared their properties at redshift 0 to see how the properties are different depending on which feedback prescriptions and kinds of feedback were incorporated. And these 13 galaxies were really different in many different properties, including that they had a range of stellar masses about an order of magnitude different and a star formation rate about 2 orders of magnitude different. So this really undercuts the predictive nature of simulations if you end up with a range that is like 1 or 2 orders of magnitude. So this kind of shows that the uncertainties, well, it's important to incorporate all feedback mechanisms, and then how you do it, the prescriptions you use, can actually really change the kind of galaxies that are produced. So we want to incorporate many mechanisms. I think there's lots of examples of this work being done from a theory perspective. One that I'm highlighting here is Ronner et al. 2017, who did semi-analytic models looking at different feedback mechanisms and showing how the forces for the mechanisms changed as a function of, for example, stellar age, which is the x-axis, or stellar mass that's considered. So the top plot is for 10 to the 5 solar mass cluster, and the bottom is 3 times 10 to the 7. And you see that which ones dominate actually changes with time. So that's kind of nice, a nice way we can consider the impact of different mechanisms from a theoretical perspective. From the observational perspective, again, multi-wavelength constraints are very important in order to have our full view of the elephant/galaxy that we're looking at. And then we want to be able to do that from many sources so that we can see what the impact is depending on ages of the stars, the conditions, the environment, etc. So with all that in mind, that was how my group began to look at the relative role of different feedback mechanisms in star clusters, was to measure the pressures associated with various mechanisms using multi-wavelength data. And so we considered a few different mechanisms when looking at star clusters in the Milky Way and the Magellanic Clouds. So we looked at the direct radiation from stars that coupled to gas. You can obtain this by getting the bolometric luminosity of the stars and the placement of them in the star cluster and where the gas is. You can obtain this using optical photometry or using radio observations of the free emission of H2 regions, which from that you can get the bolometric luminosity. So you either need optical or radio data in order to assess the direct radiation pressure. The dust process radiation, so this is, you're gonna need infrared observations to evaluate this term, in particular mid-infrared observations, and doing IR-SCD modeling lets you evaluate the radiation that's absorbed and re-radiated by the dust. If you want to evaluate the photoionized gas, that produces a warm gas pressure, which is 10 to the 4 Kelvin. In order to evaluate that, you need to get a measure of the electron density of that warm gas. And you can get this from radio or optical or infrared line ratios. And then finally, if you want to evaluate the stellar winds or the supernovae, which shock heat gas, then you really need X-ray observations. So you can do X-ray spectral modeling of the Bremsstrahlung continuum, and that gives you the density and temperature of that hot gas. So we initially did that analysis back now almost a decade ago, I'm getting older, and measured the pressures associated with these 4 terms for 32 sources in the Magellanic Clouds with this range and radius 3 to 200 parsecs and density of about 1 particle per cc. And we found that in general, the photoionization heating, the warm gas pressure is what dominated. It was 80% of the total pressure, that is the orange points. Then the dust process radiation and the winds and supernovae only contributed about 10% to the total pressure. And then the direct radiation pressure, the blue points, only contributed like 1%. So, but really we were interested in seeing how these terms change as a function of conditions and age. So with that in mind, Grace Olivier went and analyzed a sample of compact H2 regions in the Milky Way and evaluated these pressure terms and found very different results. So now we have the Magellanic Cloud results on the bottom right, and then Grace's sample on the top left. And she found that for this sample, which is much younger, so you have smaller sources that are still in very high density media, then the dust process radiation is actually what dominates. And it dominates over the photoionization heating, the direct radiation. And then we actually weren't sure of the contribution of those stellar winds because none of the sources were X-ray detected. So we could only set upper limits on those, on that pressure term. But in general, you can see that these pressure terms change as a function of size if we plot them together. And in general, you have that the dust process radiation, the red points dominates until some transition point where the photoionization heating, the warm gas pressure takes over. So smaller sources that are more obscured are dominated by their dust process radiation. And then at a radius of a couple parsecs, then they transition to being warm pressure dominated. So this was since then, a few other groups have done kind of similar analysis on different samples. And so one example of this is Ash Barnes et al. In 2020 did a similar pressure analysis for H2 regions that are in the central molecular zone of the Milky Way, the inner 100 parsecs. And so he measured the direct radiation pressure, and the warm gas pressure pH2 for that sample, and then compared it to my sources from the Magellanic Clouds on the bottom right. So he found kind of a similar trend where you had the radiation pressure dominating and then having a transition point where the warm gas pressure takes over. So the other way that one can do this analysis is using integral field spectroscopy. So in general, IFU data is very powerful because you can characterize the stellar content that powers an H2 region, and then also measure the gas properties, specifically the density and kinematics, and that can give you a constraint on the pressure terms from the different feedback. So the first time that I'm aware that somebody did this was Anna McLeod in 2019, who looked at a few different H2 regions in the Magellanic Clouds. And so this was the general trend of her result, was that again, the warm gas pressure dominated over the hot gas pressure and the radiation pressure terms. So again, she's looking at sort of larger H2 regions where the warm gas has taken over already over the radiation. Okay, so yes, yes, IFU data is beautiful. It's true. I believe that it is. Yeah. Okay, so we are actually now in an era where we can do this from many different sources. So on top of doing surveys with ALMA and JWST, FANGS has also done a FANGS Muse survey, so mapping the same 19 star-forming disk galaxies, and they've obtained 1.5 million spectra for across these galaxies at a spatial resolution of 50 parsecs. This sort of shows you how this data compares to other IFU surveys that have been done. So the number of spatial resolution elements as a function of spatial resolution, where the green points represent surveys where you have scales below like GMC scales, and then the other points on the right are sort of where you have kiloparsec scales. And so this sort of shows you how the FANGS Muse data lives up, that it has a lot of data at very good resolution. And I'll also mention that these data are all publicly available, so if you wanted to go play with them, you could. So, and this is just an example of this IFU data. One of the FANGS galaxies 4535 and GC 4535, you can get a lot of information about the gas kinematics, the stellar kinematics, the ratios of the emission lines, and all different kinds of sources that you could look at. in these galaxies or behind these galaxies. Okay, so we have this beautiful data. Now let's go play with it. So Ash Barnes then used the FANG's MUSE data and looked at 6,000 H2 regions and measured the pressures associated with these feedback terms. So again, doing a similar analysis, looking at the radiation pressure, the warm gas pressure, in this case, looking at the wind, the ram pressure, and then he also looked at the dynamical equilibrium, the confining pressure. And here, the results actually depended on what assumption of electron density he made. So if he assumed like a smooth electron density, which leads to an overall lower electron density, then the warm gas pressure dominates. However, if you assume a more clumpy density medium, which leads to higher electron densities, then your terms are a little more comparable. However, it does seem like, in general, it's pretty consistent with the previous results that the warm gas pressure is what's dominating in the sample. So that's kind of what's been done. I think in the very near future, we're going to have local volume mapper with SDSS5, which is going to be able to do this across a very large sample of local group regions, including those in the Milky Way, as well as the Magellanic Clouds, and then connect the small scales to the larger scales to understand what's happening. So I think the IFU data there will be very powerful at doing similar kind of pressure analysis. The other area of research related to stellar feedback that I'm excited about is actually more related to cosmic ray feedback. So I've kind of neglected cosmic ray feedback besides saying that theorists have been thinking about it, and really, I think a lot more observational constraints are needed. And I think in regard to cosmic ray feedback, gamma ray observations are crucial because that is where you can observe emission associated with cosmic ray protons that dominate the cosmic ray population. So currently, we're looking at it from two perspectives. On the scales of individual star clusters, we're looking at the gamma ray emission from Milky Way star clusters where supernovae have not happened yet, so that are less than 3 megayears old, where only stellar winds are accelerating cosmic rays. And we're finding that among these star clusters, a large fraction of them are gamma ray emitting and thus are effectively accelerating cosmic rays. And that's important because galaxy formation simulations currently do not account for that contribution. So this is an example of one source, M17, that we find has a 7 sigma detection in gamma rays. So it is accelerating the cosmic rays. We've also started to look at nearby galaxies. So this is the Fermi gamma ray map of the Small Magellanic Cloud. And you see that it's very spatially correlated with the H alpha emission. And so you have gamma rays that are highly correlated with the massive star formation. And we can use the spatial extents to constrain the cosmic ray transport and escape. And these are important to actually test all of that theory that's coming out in the last few years. Okay, so I wanted to switch gears a bit and talk about larger scale feedback. So that is galactic winds and outflows. So galaxy scale outflows are also driven by massive stars, and star formation driven winds are ubiquitously observed both locally and farther out. The prevailing picture is the outflows are driven by hot gas shock heated by supernovae that then entrain dust, cold, and warm gases in the flow. However, obviously cosmic rays can also be important in driving winds, radiation as well. So there's a few different possibilities here, but there's many open questions related to galactic outflows. And in particular, I'm interested in it from the perspective of the multi-phase medium and how the hot wind couples to the cooler clouds, how the winds evolve as they go out, and how they effectively transport metals from the disks of galaxies out to the CGM. So in general, I began thinking about this question, like OSU is very interactive and there's a lot of people who work on M82. And so they kind of like indoctrinated me into thinking I need to work on M82. So that's kind of where this all came from. And in general, also, I realized as they started talking to me about M82 that there's tons of deep X-ray data to try to answer these questions. But like the Strickland papers that are like the historical ones that everyone references related to the hot gas and outflows, they actually only focus on the central 500 parsecs of a galaxy. So like in M82, they only focus right on the center here. But the data is actually deep enough that you can go many kiloparsecs out and study the gradients in the properties of these outflows. It's also worth mentioning that the Strickland papers were written in like the mid 2000s, and now the data is like 10 times deeper than it was what was published in the Strickland papers. So there's a lot of ground here that we can do. So learning that and then also getting indoctrinated into thinking M82 is cool, which it is. That's what led me to looking at this. And so in a paper from 2020, I analyzed the Chandra X-ray data. Again, this is 10 times deeper than the Strickland Heckman 2009 work. And what we did was we extracted spectra, X-ray spectra across 11 different regions, going about 2.5 kiloparsecs out from the disk. And for those of you who don't know X-ray data, in general, X-ray CCDs are like IFU data where you can actually get a spectrum from any location and then model the spectrum to get the thermodynamic properties of the gas. So it's pretty cool. So these are what the beautiful spectra look like. You have a thermal Bremsstrahlung continuum, and then you have emission lines from the metals that are in the hot gas. So you can constrain the density, the temperature, and the metallicity of this hot gas as a function of the distance from the disk. So we did the X-ray spectral modeling of those 11 regions, and these are plots of the metallicity as a function of distance from the disk. So R equals 0 is the disk, and then the minuses are going to the south, and the pluses are going to the north. And in general, you see that a lot of the metals, specifically the intermediate mass elements, oxygen, neon, magnesium, are all pretty flat profiles. And then you actually have kind of peaked profiles for the silicon and the sulfur. This is because the silicon and sulfur are mostly coming from the hottest component, which are going to be enriched by the supernova ejecta, whereas these other elements are mostly being traced by the warm, hot phase, and that's why you're getting a flatter profile for those. So in general, what you see here is that these metals are being pretty effectively transported out from the disk, right? Like you're having these pretty flat profiles and it's holding pretty constant going that far out. The other profiles that we produced were the density and temperature profiles. And so these are the plots. You have temperature on the left, density on the right, and the black points are what we're able to get observationally. And for comparison, you have in the solid lines what you would get from the Chevalier and Clegg sort of adiabatic expansion of a spherical wind. And you see that the profiles are much more narrow than what we observe. So in general, this means that there must be other things happening. Specifically, you can have mass loading mixing with the cooler phase. You can also change the wind geometry, which has been done in several recent papers by Dustin Nguyen and Todd Thompson, where you can get these much broader profiles. Okay, so, after this indoctrination of M82 being important, then I was like, okay, there's a lot more sources we can look at besides this one. And so now we're doing this for an extended sample of 16 nearby edge-on starbursting, star-forming galaxies that span a range of conditions in terms of stellar mass and star formation. So these are just some of the pictures of these galaxies. Some of them have actually really deep data that have never been analyzed. So it's pretty exciting. And so the second one that we turned to was NGC 253. So this is a paper led by OSU graduates and Sebastian Lopez. I was very excited to write a Lopez and Lopez paper. So, woo, life achievement unlocked. Okay, so we analyzed NGC 253, and the blue are the X-ray data from Chandra. Again, I think this is 8 times deeper than what had been published before. And so you can see the outflows going. We're able to measure up to like a kiloparsec away from the disk. Like our work with M82, Sebastian went to produce the profiles of the metallicity, but also of the temperature and density of the hot gas. And the black points are the profiles that he produced. And again, we see that the Chevalier and Clegg models are giving narrower profiles. You end up with something that is that sort of falls off with radius much more steeply than what we observe. However, if you use Dustin's new models, then which take into account a non-spherical geometry and can include mass loading, then you end up with these broader profiles like what we observe. So as I mentioned, we're in the process of doing this for the larger sample to see how the galactic wind properties change for different galactic properties. The other thing we're interested in is understanding the multi-wavelength, multi-phase nature of these winds. And so there's a lot of beautiful H-alpha data that has been taken. We're excited to work with Drummond on that. In addition, Alberto Bellato has recently gotten JWST observations of M82 and soon NGC 253. So this is a bit of a advertisement slash pretty picture from this JWST program, where you can see the 3.3 microns, which is tracing the PUHs, the polycyclic aromatic hydrocarbons, in the disk of M82, and its relationship to the hot gas from the Chandra observation, as well as the warm gas in HST. And it's amazing because we see these sort of like chimneys of dust features that are coming out of the disk. And so I don't know what's happening there. And we're basically beginning to do this kind of multi-wavelength analysis to really understand how these phases are connected to each other, how everything gets out of the disk, and how it's connected to, the stars that are starbursting in the disk. The other thing that we're excited to look into is actually how metal loading changes with different kinds of galaxies, host galaxies, stellar mass, as well as the star formation rate of the galaxy. This is a particularly interesting question to us because recent work on the warm phase of galaxies has shown that the metal loading, which in this plot increases going downward, actually increases for smaller galaxies. So they find that in the outflows of the warm phase, and I think we actually find the opposite for the hot phase. And so this is sort of to highlight that it's very important to actually get constraints of all the phases, see all sides of the elephant in order to understand what's happening, and see how effective these metals are being transported out of disks, but also what phase they're in as they get out of the disks. The other thing that is on the horizon is the launch of CRISM, which is the Hitomi replacement mission. So Hitomi was the microcalorimeter, X-ray microcalorimeter that was launched by Japan, and then it broke. And they basically built another version of it, and it's just being launched again. And hopefully will not break this time. And the reason why it's exciting is because it is the first time that you can get high resolution X-ray spectroscopy of extended sources like galactic winds. And so when you have very good spectral energy resolution, you can go from a spectrum like that's plotted on the top to a spectrum that's on the bottom. So you can actually see these individual oxygen lines. And when you're able to disentangle them, then you're able to get velocity information. So we can get another constraint for galactic winds that is not just get the profiles of the density and temperature, but also see how fast the material is moving, and even possibly how fast different metals are moving. And that's just another way that we can understand winds better and how they're launched from galactic disks. So CRISM is due to launch in 2023, so this year, and we're going to get the first observations. M82 is one of the first targets. So I think, we'll learn even more about the wonders of M82 with those observations. So I already gave you my conclusions, so I'm not going to reread them, but this is just to say that hopefully you feel now that feedback is important, but there are many ways that we can kind of try to tackle it from a theory perspective and from observations, and actually put those two things together to learn even more about their impact on small scales up to larger scales. Thank you.
And do we have questions for Laura? Sarah's hand first.
Very nice talk. I was curious about the spatial distribution. You were saying about different types of supernovae obviously explode different locations.
Yeah.
So some can't travel very far. So I was just wondering, are we at the stage now where it's important theoretically to actually distinguish between what type of explosions are happening in randomly distributed versus in the disk? And is that something theorists are already modeling?
Yeah, so I think it is important to consider what kind of supernova there are and where they are occurring. And I think, maybe Matt can correct me, that Fire 3 is incorporating some of that into the new simulations. That is, like, that type 1As are more randomly distributed and core collapses are maybe more concentrated in disk, but they are starting to take it more into account. So I think that's good, because I think it is important, and it does change what the feedback is doing. So I think people are starting to do it, thankfully, just in the last few years.
Sal Blakesley, and then we'll go with Rachel. And Mordecai.
So some of the UV data is probably like a mix of like Galax and maybe some costs. Like if you had a wide field of view, cost like spectral resolution with a long slit, what would what would that enable, like in the UV? Because I feel like the UV is probably one of the weaker links in terms of the multi-wavelength spectra that you have.
That's definitely true. So if you have something like the proposed Hyperion mission, what could it probe? And let's see, so it was doing the far UV, which is fairly under constraint. Well, I think it is the weakest link, so to speak.
Like Lyman alpha, Lyman continuum, like high spectral resolution.
Yeah. So, I mean, I think you're basically tracing part of the medium that you didn't get before. So it's giving you a more full view of the elephant. And I have to think more about what you would learn from it, but I think it's definitely something that isn't probed currently. And so, yeah, I think you'd get more out of it.
We'll do Rachel, and then we'll go to the Zoom room.
So thank you, beautiful work and lovely talk. I noticed that one of the things you did not mention was something that as theorists we obsess about a lot, and that's mass loadings and energy loadings. Is that because you think we just can't measure them observationally, or just because you made a choice not to talk about that?
Yeah, so that's a good question. I think we can constrain mass loading and energy loading, and we just haven't done it yet. But I would like to, I want to, I'm talking to Drummond. And so I think, yes, absolutely, we should. And that is something we want to do in the future.
I mean, if we're starting to have this multi-phase
Yes.
data for more galaxies, then we have a great.
Yes.
I found that encouraging.
Absolutely.
Great, thank you.
And Mordecai?
If I can ask two questions. The first one is when you are looking at the coincidence of supernovae with dense gas, it looked like you were looking at a 2D coincidence.
Yes.
But of course, dense gas has a very low 3D filling factor. So and if I go back and look at the old paper by Youssef Zada et al., that had like a factor of 2 lower coincidence factor with dense gas by following masers. So are some of these coincidences truly just coincident line of sight coincidences on what looks like somewhat low resolution for the purpose measurements of the dense gas?
Yeah, so I think that is a risk, and I guess one comforting thing I can say here is that the FANG's ALMA survey was face-on galaxies, so you do have less line of sight effects than you would otherwise.
Sure.
But I think that's also part of the motivation of having a larger sample size, is because then you'll be less impacted by that. But that is certainly a risk, is that maybe something is in the foreground, and thus these are actually limits on what the associations are.
Just to be contrarian, it is a more actively star-forming galaxy than the Milky Way with all these supernovae. So
yes, for sure.
maybe they really are more associated just because there is more dense gas. Okay.
Mm-hmm.
The other question I wanted to ask was about your bubbles and bubbles.
Yep.
Were those bubbles identified kinematically with IFU data or just by looking for circular structures? That is, are they expanding?
So I think they did confirm the bubbleness of the bubbles using the Muse data. So they did use some of the complementary information to confirm the bubbleness.
Thank you.
Yep.
Great work.
More questions from the room?
Thanks for great pictures. Also related to the bubble. So do you know that these are supernovae feedback? Like, how do you say that? What sort of traces do you know to say that they're supernovae feedback? And the reason I'm asking is because of like the local bubble in the backyard. Like the theory is that it is supernova feedback, but we really just don't know.
Yeah, that's a very good question. I would say in general, another piece of complementary information that we have is HST observations, where we can look at the stellar populations that are powering these bubbles and sort of see their ages and know, yes, they are old enough to have had supernovae occur. So I think that's one of the constraints. Yeah, so I would say the complementary information is important there.
And these studies have been done, so Dan Weiss did some stuff with this earlier, Steve Warren, where we've done, galaxies that are typically closer than FANG, so you can actually see a little bit, further down the mass function of the stars. And you don't find super young clusters, but if you analyze the star formation history, it's often like 25 million years, 30 million years. Like, there's definitely elevated bursts of star formation, but it's not like you see a hot pocket of stars sitting in the top. So it'll be interesting to see with the FANG's HST data, like, do you get deep enough down that you can pick that up? But
Yeah.
the closer ones, it seems pretty consistent.
And Lachlan?
I was wondering in Grace's work, you mentioned that most of the X-ray constraints are just upper limits. What are the prospects for actually constraining the X-ray properties in the future?
I was hoping that you would hear me say that. I think I might have even looked at you when I said it. And so, yeah, I think in general, those were not relatively deep observations, so we could get it. However, we are limited a bit by the spatial resolution as well. But I think it would call for targeting the closer sources with longer observations, and then it could be possible.
Anyone else from the room? Perfect. Well, I think that brings us to the perfect timing for the reception outside. There are food and drinks and plenty of time to chat with Laura and everyone else here. So thanks again for our speaker, Laura.